Example 2. For the region S in example 1, we want to show that the sum of the areas of the upper approximating rectangles approaches 1/3. And that is, if we take the limit as n approaches infinity of the right endpoints with a subscript of n, does that equal 1/3? So here is our graph. Here's our rectangles. Again, we're using y equals x squared, and we're looking at the value of 1/n. So let's first talk about this. So that we know that each rectangle has a width of 1/n. Okay, so let's go ahead and write this out. We know that we're going to have r subscript n, which is going to be 1/n squared times 1/n plus 2/n squared times 1/n plus 3/n, and that's squared, times 1/n, and then continuing, we would have n/n squared times 1/n. Okay? So now let's factor out a 1/n because each particular term has a 1/n. So let's go ahead and factor that out. So if we factor out the 1/n, then what we have left is 1 squared over n squared plus 2 squared over n squared plus 3 squared over n squared plus n squared over n squared. Okay, so now we can also factor out a 1/n squared because we have a 1/n squared in each of those terms. So now we can factor out the following. It's going to be 1/n times 1/n squared. And so what is remaining? Well, what's remaining is 1 squared plus 2 squared plus 3 squared plus n squared. Okay, so at this point, this 1 squared plus 2 squared plus 3 squared plus n squared is a definition from the past here. And so I'm going to pull that up here. Okay, so here we need the formula for the sum of the squares of the first n positive integers. So the sum of the squares of the first n positive integers is equal to the following. So we're going to replace this with n times n plus 1 times 2n plus 1 over 6. So what we're going to do now is we're going to take r subscript n, we're going to multiply 1/n times 1/n squared, which is 1/n cubed. And then now we're going to be multiplying that by n times n plus 1 times 2n plus 1 divided by 6. Okay, so what can we do here? Well, we can simplify one of the n's. So if we can simplify one of the n's here, we get n squared. So therefore, we have the following. R subscript n is going to equal n plus 1 times 2n plus 1 and that's divided by 6 times n squared, which is 6n squared. Okay, so now we want to go back and talk about this limit as n is approaching infinity. So what we want to do is, we know that we're going to let the number of rectangles, which is n, is going to approach infinity. So what does that mean? That means we're taking the limit as n approaches infinity of r subscript n. So let's go ahead and do that. So what that means here is that we're taking the limit as n approaches infinity of n plus 1 times 2n plus 1 over 6n squared. Okay, so let's distribute that numerator. So we have the limit as n approaches infinity. If we distribute and multiply that, we end up getting 2n squared plus 3n plus 1 over 6n squared. Okay, so the highest degree in the denominator is n squared, so that means that we're going to multiply the numerator and the denominator by 1 over n squared. So we take the limit as n approaches infinity of 2n squared divided by n squared plus 3n divided by n squared plus 1 divided by n squared, and in the denominator we have 6n squared divided by n squared. Okay, so now when we simplify this a little further, we get the limit as n approaches infinity of 2 plus 3 over n plus 1 over n squared divided by 6. So now if we take the limit as n approaches infinity, we're going to get the following. We're going to get 2 plus 0 over 6, which gives us 2 over 6, which reduces to 1/3. So therefore we can say that the limit as n approaches infinity of Rn is going to equal 1/3.